So good day to Puan Shadila Miss. So my team consists of myself, Visves, Mughesh, JaYneSh and Thiva. So today we're gonna do a virtual presentations about our mini project of the FC 30233 data structures. So here we go with situation 1. So Miss can ask me what is about situation 1. So situation 1 is about data structure course have 8 classes. So that's the situation lah. So each class can hold a maximum of 30 students only. So the already mentioned 30 students. Assuming in case JaYneSh want to store a final examination marks of his class, and the way in case JaYneSh stores the data in random and not necessarily to sort from highest to lowest. So from this question we need to take some important points. Number 1, 30 students. So they already mentioned it. And then for this I think stack will be the best. Why stack? Okay, stack when we use stack, the first thing we need to know is the maximum size. What is the size of the stack? So from this question I already know that 30 student is going to be the size. So I assume stack can be the best. Second thing, stack is the LIFO. What is LIFO? Last in, first out. That means the person who come at the last will be served first and the person will be out. So since I'm going to use stack, right, so the explanation is we can create a stack for each class to store the final examination marks of the students. So each stack will present a class and we will push the marks onto the respective stack. Since the order of storing the marks is not sorted, so you need to take these points, it's not sorted. Then using a stack inappropriate as it follows the last in first out principle by setting every class max capacity is about 30. So my example is here. As you can see, there is a 8 class and you can see the stack size is about 30. So the lecturers or interior designer or all the teachers, right, can input the marks and can delete input. So since we know the maximum size of the stack, we know that it's going to be the marks we can put inside and we can take it out in a simple way. So that's the explanation from me. So my answer for this video is about stack. Thank you.
Okay, thank you to the Visves for explaining the situation 1. Now I'm going to explain the situation 2, which is data structure queue. Explanation. A queue is a linear data structure that follows the first in first out FIFO principle. It means that the first element added to the queue will be the first one to be removed. In this context, the printer can be represented as a single resource and the queue will help manage the printing requests from different computers in an organization and fair manner. For the process is when an employee sends a printing command from their computer, the command is added to the end of the queue. The printer processes the command sequentially, starting from the front of the queue, i.e. the first command that was added. As soon as the printer finishes the processing as command, it is removed from the front of the queue, and the next command in line, if any, becomes the next one to be processed. Okay, this is the example for the situation 2, which is got 6 lists, which means 0, 1, 2, 3, 4, 5. So when we see, we have the in 0 got computer 2, in 1 got computer 3, in number 2 got computer 1, in number 3 got computer 5, in number 4 got computer 4, in number 5 nothing. When we see the computer 2 is front right and the 5 is rear. So when you see the printer, after printing the computer 2, the computer will become deleted and computer 3 will become to number 0. so it will become to front, and after that all the process will become to front, and number 5 will be the rear. So which means the computer 3 will be become 0, and computer 1 will be become 1, and computer 5 will become 2, and computer 4 will become 3, and number 4 and 5 list will become a 0. It is a FIFO when we apply in the process of queue.
So for the next one is situation 3. In its file management system, an operating system may utilize a hierarchy tree like data structure for directories, files, and folders. Common names for this structure include file system tree and directory tree. It employs a hierarchical organization scheme for files and folders. The root directory from which all other directories and files branch out is the highest node in the tree. Subdirectories of the directories may contain further subdirectories and files, creating a structure resembling a tree. Here's a simple representation of what is a file system tree might look like. So, if we see the uh, file system tree, for the first one is the folder, and it became a two, which is folder A and folder B. So these are the things which is the subdirectories of the directory, which is the folder. So the folder A also became two files, which it also has the subdirectories, which is file A, file 2, and also for the folder B, it has subfolder B1 and also file 3. So for the subfolder B1 also got the file 4. In this example, the root directory contains two main folders, folder A and folder B. Folder A contains two files, which is file 1 and file 2, and folder B contains a subfolder, which is for subfolder B1 along with file 4. Subfolder B1 contains file 3. User and the operating system can effectively browse the directory structure, access files, and manage the organization of data thanks to the file system tree. The core principle of a hierarchical directory structure is the same regardless of the modifications that different operating system utilize to implement it. Using a tree data structure for organizing directories, files, and folders in a file management system offers several advantages, which is for the first one, hierarchical organizations. The way that files and folders are commonly organized and in real life systems is similar to the hierarchical organization that tree naturally give. The relationships between folders and files may be logically and intuitively represented thanks to the hierarchical structure. Efficient searching and access. Trees provide for effective access in searching, finding a specific file or folder from the root directory may be done for balanced or unbalanced trees in a time complexity. Due on this, even in huge file systems, certain files may be found and accessed quickly. So for the third one is space efficiency. Tree data structures can be relatively space efficient, especially compared to flat structures where all the files are stored at the same level. In a tree, files are and directories share common parent directories, which can save space and make the file management system more scalable.
Now I want to present about situation 4. The backward button will always function as interior and return you to the previous page in the order you accessed them if you use a stacked data structure. The browsing history of the web browser like Google Chrome may be easily managed and navigated using this feature. The stack will be represented as follows. This is the stacks: tab C, tab B, tab A, and new tab. So initially the stack is empty. The user opens a new tab with no browsing history. When the user visits tab A, it becomes the top element most recently visited page in the stack. Upon visiting tab B, it becomes the new element in the stack. Subsequently, when the user visits tab C, it becomes the top element in the stack. If the user clicks the backward button, the top element website C is removed from the stack and the user taken web to website B. Next, tab B, tab A, new tab. This is the top tag of the current page. If the user clicks backward button again, the top element tab B is removed from the stack and the user is taken from back to tab A. The next one is tab A, new tab. This is a top stack of tag current page also. The top element tab A is removed from the stack and the user is returned to a new tab if the present is backward button once more. The next one is new tab. Now the user is back to website A. The stack contains only one element representing the current page. By keeping track of the user browsing history and enabling quick access to previous pages in reverse order of access, the stack data structure makes it possible for the backward button to function effectively.